Now next is conductor free space boundary condition. So instead of dielectric and conductor free space, conductor dielectric, we are considering the case of conductor free space boundary condition. For studying for this also, we are taking the same equations, integral E dot dl equal to 0 and integral D dot ds equal to q enclosed, the same we are considering. And here also E is decomposed to Et and En, so E is equal to Et plus En. Now the conductor is considered as ideal, that is having infinite conductivity, so E, D and rho V within the conductor is 0. For finding that boundary condition, we are considering this figure. In this figure, for finding the equations related to E, we are considering the rectangular path, and for equations related with the D, we are considering the pillbox. So in the rectangular path, it is ABCD, it is in clockwise direction, it is marked. Height is delta h, width is delta w, and E is resolved into 2 Et and En. In case of pillbox, it is having a height delta h, surface area is del s, and with corresponding to D, it is resolved into 2 dn and dt. And in this, the lower part is considered as conductor and the upper part is considered as free space. So considering the rectangular path ABCDA as shown, we can write integral E dot dl equal to 0. It means it is splitted A to B, B to C, C to D and D to A. Same style which we did in the previous derivations. So integral A to B EDL plus integral B to C EDL plus integral C to D EDL plus integral A to B EDL is equal to 0. Now what is delta H delta W? It is the elementary height and elementary width. Now half of the rectangle is in the conductor and the remaining half is in the free space. So CD path can be made equal to 0. Why? Because E is 0 in the conductor. So integral A, the equation becomes integral AB EDL plus integral BC EDL plus integral DA EDL equal to 0, and integral CD EDL is equal to 0 as E 0. So it is not included in this. Now integral A to B EDL is equal to integral A to B E integral A to B DL. Now what is DL over there? A to B is in widthwise, so DL can be written as delta W, so it is E delta W. Delta W already mentioned, tangential, it is in tangential direction to the boundary, so E can be written as ET. So integral AB DL can be written as ET delta W. Let it be your second equation, and ET value is mod of ET. Now BC, in case of BC, it is parallel to the normal component, so E is equal to En, and it's over the height delta H. And BC EDL, it can be written as E integral BC DL, and it is equal to En integral BC DL. Why En? It is normal, so that E is replaced as En. Now in case of BC, B to point 2 is in the free space, and from point 2 to C is in the conductor. You can see from the figure there are 2 points marked at the interface 1 and 2. So while taking the path BC, it can be divided into B2 and 2C, B2 and 2 to C. So and in that 2.2 to C is in the conductor, and there E is equal to 0. So integral B to C EDL, can be equated as, it is equal to integral B to 2 EDL plus integral 2 to C EDL. As E is 0 in conductor, integral 2 to C EDL is equal to 0. Therefore integral B to C EDL can be written as, that is equal to En del H by 2. Now how it came? Integral B to C EDL is equal to, we know the 2 halves and the second half is equal to 0 already. Integral B to 2 E del H by 2 is the remaining. So after integrating, we get that E is named as En, as it is in normal En del H by 2. That is your third equation. Now for path third, DA condition, DA, the condition is same. So integral D to A EDL, that is equal to minus En del H by 2. That is your fourth equation. Then Why negative? It is because the direction is opposite. So substituting these three equations in the first equation we can write Et del W plus En del H by 2 minus En del H by 2 equal to 0. So both that get cancelled. So the equation becomes Et del W equal to 0. That means Et is equal to 0. Thus, tangential component of electric field intensity is 0 at boundary between conductor and free space. Thus, E at boundary between conductor and free space is always in direction perpendicular to the boundary. Now, D is equal to epsilon naught E. Therefore, if Et is equal to 0, then dt is equal to epsilon naught Et. That is also equal to 0. Thus, tangential component of electric flux density is also 0 at the boundary between conductor and free space. Now to find the normal component, consider the pillbox in the figure. In the form of right circular cylinder, height is delta h. It is placed such that delta h by 2 in the conductor and another half delta h by 2 is in the free space. And the axis is normal to the surface. Surface is delta s. From the equation, integral d dot ds equal to q enclosed, the surface integral must be evaluated over three surfaces. We have three surfaces: top surface, bottom surface, and lateral surface. So the equation can be written as integral top d dot ds plus integral bottom d dot ds plus integral lateral d dot ds is equal to q. That is your fifth equation. Now the bottom surface is in the conductor where d is equal to 0. Therefore, the above equation can be written as integral top d dot ds plus integral lateral d dot ds equal to 0. That is your sixth equation. Now the lateral surface area, it is 2 pi r del h, where r is the radius of the cylinder, and del h, as it tends to 0, area reduces to 0. Therefore the equation becomes integral top d dot ds is equal to dn integral top ds, that is equal to dn delta s, and that is equal to 7q. That is your seventh equation. Now why d becomes dn? It is normal, so it is taken as dn, and ds, it is already marked in the figure, it is surface is delta s. So at the boundary, charge exists in the form of surface charge density rho s, coulomb per meter square. Therefore q is equal to rho s delta s. That is the eighth equation. So equating both 7 and 8, because there is q in both equations, so equating both, you can write dn del s is equal to rho s del s. Cancelling del s, you can write dn is equal to rho s, and dn is equal to epsilon naught en, and that is equal to rho s. If d is equal to epsilon naught e, we can write dn is equal to epsilon naught en. So dn is equal to rho s, therefore epsilon naught en is also equal to rho s. From this you can find the equation for en. En is equal to rho s epsilon naught. Thank you.